You ever stop and wonder what's really holding a skyscraper up? Or what gives a bungee cord that incredible thrilling snap? Well, it's not magic. It's physics. Today, we're going to pull back the curtain and meet the invisible architects that shape our entire reality. These are the fundamental forces that are always at play, designing our world from the ground up.
So let's start with a bit of a riddle. What could a coconut falling from a tree and a massive, sprawling steel bridge possibly have in common? I mean, they seem like they're from completely different worlds, right? But here's the secret. They're both governed by the exact same invisible rules. Stick with me, and by the end of this, you'll see exactly how they're connected. It's going to be cool. To get why anything moves, or, just as importantly, why it stays put, we have to start with this one big idea, the resultant force. Just imagine an object being pushed and pulled in all sorts of directions at the same time. The resultant force is like the final score. It's the single overall force that says, okay, after all that pushing and pulling, this is what's actually happening. It's the bottom line. So how do we find this super important resultant force? Well, let's think of it like a giant game of tug of war. To figure out who's going to win, you just need to know a few simple rules for how the teams combine their strength. Honestly, it's pretty straightforward. When forces are pulling in the same direction, they're on the same team, so you just add their strengths together. Simple. When they're pulling in opposite directions, they fight it out, and you just subtract the weaker force from the stronger one to see who wins and by how much. But what if they're pulling at an angle? Well then, they team up to create a new diagonal force, and we can figure out exactly how strong that is with a little bit of vector math. Often, it's as simple as that Pythagorean theorem you probably thought you'd never use again. And this is the absolute key to everything. If that final resultant force isn't zero, if one side of the tug of war is even a little bit stronger, then the object's motion has to change. It's going to speed up, slow down, or change direction. This is literally the heart of Newton's second law. An unbalanced force always causes acceleration. No exceptions. Okay, but what happens when the forces cancel each other out perfectly? What if our cosmic game of tug of war ends in a total and complete stalemate? Well, that's when we reach the state of perfect balance, a state that physicists call equilibrium. So equilibrium is that special state where every single push is perfectly matched by a pull. Every lift is countered by a weight. All the forces are so perfectly balanced that the resultant force, that final score, is zero. You can kind of think of it as the Zen state of physics, right? Total harmony, no overall push or pull in any direction. Now hold on a second. This is a huge trap. It's so easy to think that if all the forces are balanced, the object has to be completely still, not moving at all. But you know what? That's not the whole story. Just look at these two situations. You've got a book sitting on a table. It's in equilibrium, for sure, and yep, it's stationary. But now think about a car with cruise control on. The forward push from the engine is being perfectly canceled out by the backward drag of air resistance. The resultant force is zero. That car is obviously moving, but, and this is everything, it's moving at a constant velocity. Equilibrium means zero acceleration, not necessarily zero speed.
So we've talked about when forces are balanced, but what about forces that actually try to restore balance whenever they get disturbed? That's where we get into the amazing world of elasticity. It's the force that lets things be stretched and squashed, and then just snap right back to where they started. And this brings us to this incredibly powerful but simple idea called Hooke's law. All it's really saying is that how far you stretch something elastic is directly tied to how hard you pull on it. Double the force, you get double the stretch. It's this beautiful, predictable relationship that's running everything from a simple rubber band to the suspension in your car. The formula looks like this. F equals K times X. F is the force you're applying. X is how far the spring stretches. So what about that K? Well, K is the spring constant, and you can think of it as the spring's personality. A really high K means you've got a super stiff spring that's tough to stretch. A low K means you've got a looser, more flexible spring that stretches pretty easily. So what gives a spring its specific personality? As you can see here, it's all about its physical DNA. Springs that are shorter or made of thicker wire or have a tighter coil are all going to be stiffer. They'll have a higher K value. And these are the exact things engineers play with to design springs for super specific jobs, from the tiny clicker in a pen to the massive suspension on a train. So when you stretch a spring, you're putting in work, right? You're investing your energy into it. And that energy doesn't just vanish into thin air. Nope, It gets stored inside the spring as elastic potential energy. It's just sitting there, waiting for a chance to be released. This is the whole idea behind a slingshot, or even the tiny gears in a wind-up watch. Now, the formula for all that stored energy is 1/2 kx squared. And the most important thing to see here is that the stretch, the x, is squared. This is a huge deal. It means if you double the stretch, you don't just get double the energy. You get 4 times the stored energy. It's an exponential relationship, and it's what makes elastic things so incredibly powerful.
Here's a cool little trick to help you visualize that energy formula. If you were to draw a graph of the force you apply versus how far the spring stretches, you'd get a perfectly straight line. Well, the elastic potential energy you stored is simply the area of the triangle right under that line. It's a fantastic way to actually see the concept. And honestly, it helps you avoid making silly mistakes when you calculate it. All right, we've talked about resultant forces, that perfect balance of equilibrium, and the hidden power of elasticity. It's time to put all the pieces together and go all the way back to our very first question. So, what was the deal with that giant bridge and the falling coconut? Well, they're actually perfect opposites that prove the exact same rule. The bridge is a masterpiece of equilibrium. Its designers have calculated every single force so that the final resultant force is always 0. That's why it's so stable. The coconut, on the other hand, has a big, unbalanced resultant force acting on it. We call it gravity, and that's exactly why it accelerates towards the ground. So let's wrap this up with your new physics toolkit. First, remember forces have direction, so you always have to treat them like vectors. Second, it's only a non-zero net force that causes acceleration. Third, equilibrium, that sweet spot where the total force is 0, is the absolute key to stability. And finally, elasticity is just nature's super clever way of storing and releasing energy. Look, these aren't just ideas in a textbook. These are the invisible rules that literally build the world all around you. From the tension in the cables of an elevator to the suspension that gives you a smooth car ride, these forces are absolutely everywhere. Now that you know what to look for, the only real question is, where are you going to see them in action next?